Welcome to day 68. Today, we're going to break down a really fundamental architecture in language processing, the sequence-to-sequence model. It solves a very common problem that, honestly, most standard neural networks just aren't built to handle.
Think about something like machine translation for a second. How can a machine take a four-word sentence in, say, French, and turn it into a 9-character sentence in Japanese? The input and the output have totally different lengths. This kind of mismatch is exactly where a lot of models would fail. So how do you build a system that can actually do this? Well, by the end of this explainer, you'll get the elegant, two-part architecture that solves this exact problem.
Okay, the best way to get the intuition here is to just forget the technical jargon for a moment. Instead, let's imagine a human translator who has two jobs, a reader and a writer.
First, our translator reads the entire sentence they need to translate, start to finish. They're not writing anything down yet. Their only goal is to completely absorb the meaning. Once they feel like they've understood it, they put the original text aside, and only then do they start writing the translation. And they do it from scratch, based purely on their understanding. This two-step process, read then write, that's the whole essence of a seek-to-seek model.
That moment of understanding gets captured in something we call a context vector. You can think of it as a really condensed summary of the input. Sometimes people call it a thought vector. It's basically just a list of numbers that has to hold the meaning of the entire input. And here's the key part. This vector is the only thing connecting the reading phase to the writing phase.
All right, now let's map that analogy to the real architecture. Our reader and writer are actually two distinct parts of the model, the encoder and the decoder. So the encoder's job is to be the reader. It goes through the input sequence, word by word, and its only goal is to compress everything down into that single context vector. That's its only output. Then the decoder takes over. It's the writer. It gets that context vector as its starting instruction and then begins generating the output, one word at a time. And crucially, to figure out the next word, it looks at both the context vector and all the words it has already written.
Now, under the hood, what are these things? Well, both the encoder and the decoder are usually a type of recurrent neural network, or RNA. You'll often see things like LSTMs or GRUs used here. And that makes perfect sense because RNNs are built from the ground up to handle sequences, to carry a memory of what they've seen before, to inform what they do next.
So this is a pretty clever architecture. But where does it actually show up? Well, this ability to handle mismatched lengths makes it a real powerhouse for some very familiar applications.
Machine translation is, of course, the classic example. But the same idea applies to text summarization, right? You take a long article as the input sequence and produce a short summary as the output. Chatbots use it to turn your question into a reply. And it even goes beyond text. Speech recognition can take a sequence of audio waves and decode it into text, and in image captioning, you can encode a whole image into a context vector, which is then decoded into a sentence describing that image.
Now, this classic architecture isn't perfect. It has a pretty significant limitation, a bottleneck that's baked right into its design.
The problem is that context vector. It has to cram the meaning of the entire input, no matter how long, into one fixed-sized summary. For a really long sentence, that's like trying to describe an entire movie on a single post-it note. You're just going to lose some detail. And this exact limitation, this information bottleneck, is what directly led to the invention of attention mechanisms.
So, to wrap this all up, seek-to-seek models work by transforming one sequence into another. They do this by first encoding the entire input into a single summary vector, and then decoding that vector into a brand new output.
If you remember just one thing from today, make it this principle. First understand, then generate. That is the simple, powerful idea behind every single seek-to-seek model.